In the previous video, we saw that a shallow quantum well can be faithfully represented as an attractive Dirac delta potential, and in this video we're going to solve the Schrödinger equation with the delta potential in an arbitrary dimension, 1, 2, or 3. And we're going to use a very powerful method, mathematical method, that as a matter of fact was used by Leon Cooper to solve the key problem in the theory of superconductivity, the problem of electron pairing, which brought him eventually a Nobel Prize, and now this phenomenon of pairing is actually called Cooper pairing. But, well, we'll talk a little bit about this later, but at this stage we're going to focus on just a single particle Schrödinger equation with this sort of short-range attraction. And so before going through the technicalities, I want to give you the bottom line, the main result, if you sort of get lost in these technical details. So at least I would like you to know the very important outcome of this calculation we're going to see. And so the outcome would be the following. So we will see that in 1 and 2 dimensions, it doesn't matter how weak attractive potential gives rise to a bound state of a quantum particle. So it doesn't matter how shallow a well we have, it always will bind the particle. But in 3 dimensions, it turns out that if you have a very weak potential, very shallow potential, it's not enough to keep the particle, to localize the particle. And this difference, qualitative difference, actually have very important consequences in various fields of physics, so you may want to remember that. But now let me go to the technical part. Okay, so I will start with a certain math reminder, which basically will remind you what Fourier transform is. So we can solve the problem. We will solve the problem using only the Fourier transform. There will be nothing else involved essentially in this solution. Fourier transform and inverse Fourier transform. So what is a Fourier transform? So if you have an arbitrary function, well, reasonable function g of x, so in our case it will be a wave function and various derivatives of it. So the Fourier transform of this function g of x, which we call f of g of x, or g tilde of k, is an integral of g of x with this exponential. So physically, this k in our case will represent the wave vector, and h times k is going to be the particle's momentum. But in principle, you can view this Fourier transform as a mathematical procedure. And an important fact here is that if you know the Fourier transform of a function, you can restore the function itself by doing the inverse Fourier transform. So g of x is equal to an integral of, there should be g tilde of k e to the power minus I kx dk over 2 pi. So I should remind you or emphasize that where to put this 2 pi is actually a matter of convention or convenience. So we could have put the 2 pi in the direct Fourier transform, or we could have separated them sort of like this. So we could have put 1 over square root of 2 pi here, 1 over square root of 2 pi here, or any other combination of powers, so that the total power of 2 pi in the denominator is equal to 1. And this is a matter of convention. In quantum mechanics, the convention is that the 2 pi appears in this inverse Fourier transform, which features the wave vector or the momentum. So I will just erase this stuff here. So anyway, so this is what we know, and now the simplest perhaps example of a Fourier transform will be actually a Fourier transform of the delta function. So if we want to Fourier transform the delta function, we know that the delta function, when integrated in infinite limits, just picks the value of the function is being integrated with at x equals 0. So, and if we integrate delta of x with the e to the power I kx from minus infinity to plus infinity, we simply will get 1, because e exponent of 0 is equal to 1. So therefore, the Fourier image of the delta function is 1, just identity in this case space. So, and we can also do the inverse Fourier transform, which basically gives us the representation of the delta function. It's an integral from minus infinity to plus infinity of this exponential dk over 2 pi. And we have seen it already actually before. So, and these identities actually will be enough again for us to solve the problem. So now the problem that we actually want to solve mathematically is the Schrödinger equation, which is presented here. So the left-hand side of this equation here represents the Hamiltonian. So the Hamiltonian, this part is the kinetic energy, the usual kinetic energy written explicitly in the coordinate representation. So this is just p squared over 2m. And this guy is our potential, delta potential. So later on we're going to generalize it to arbitrary dimension, but at this stage I'm just doing 1 dimension for simplicity. So and of course we're dealing now with the time-independent Schrödinger equation, And the goal of this calculation, basically the goal of our derivation, would be to determine the value of the energy, and in particular, we would want to figure out whether or not there are bound states with negative energy. So essentially, if we want to sort of draw symbolically the potential that we're dealing with, so it's zero everywhere, but in the vicinity of x equals 0, there is a sharp sort of well, and the question is whether there is a bound state or bound states in this well with some negative energy. So this is basically the question. And so now let me do the actual calculation using this reminder and the Schrödinger equation. So what we're going to do, we're going to represent the psi of x as a Fourier transform of the wave function in momentum representation. So it's going to be an integral of dk over 2 pi of some psi tilde sub k, I'm going to write it, e to the power minus I kx, from minus infinity to plus infinity. And just for the sake of brevity, I'm going to call this integral as so that I don't have to write these standard factors and limits again. So it's identically equal in my notations to this. So there are three types of terms that appear in this equation. So the wave function itself appears in the right-hand side multiplied by the energy. In the left-hand side, though, we have, for instance, this guy, which is the second derivative of the delta function, psi double prime. So if we differentiate this Fourier transform twice over the coordinate, we're going to pull out, so the derivative of the exponential is the exponential itself, but we're going to pull out this minus ik squared. So therefore, we can represent this second derivative as psi tilde sub k times minus ik squared e to the power minus ikx. So this guy is the Fourier transform of psi double prime. And finally, we also have this term, so delta of x, psi of x. But since delta of x is a sharply peaked function at x equals 0, so it essentially pulls out only the value of the wave function at x equals 0. So all other values of this wave function in this product basically don't matter. So this term is going to be identically equal to psi of 0 delta of x. Okay? And delta of x, we know that the delta of x, the Fourier image of delta of x, as we discussed in the previous slide, is simply equal to 1. So we can represent this as psi of 0, an integral over k. Again, it's implied that it's from minus infinity to plus infinity, e to the power minus ikx. That's it. So this is the basically the way we can write this this equation. And so if we put everything together, so we're going to have in the left-hand side, we're going to have minus h squared over 2m psi tilde sub k minus I k squared e to the power minus I kx. So this term, the second term, is going to be minus alpha psi of 0, which here is simply a constant. So we have pulled out the value of the wave function at x equals 0, so it's just a constant. And here we have this integral e to the power minus I kx. In the right-hand side, we're going to have simply energy times the wave function coming from here, k psi tilde e to the power minus I kx. So we see that in all three terms, we have these integrals and we have these exponentials, and we can simply focus on the overall coefficients that multiplies all these exponentials and essentially get what we can call it a Schrödinger equation in momentum space. So in some sense, we can just get rid of these integrals. And let me have some space here. Let me erase most of this stuff. So as a result, if we basically look at this equation without the integrals for a particular k, so this term, the first term in the left-hand side, is going to give us now plus h squared over 2m k squared psi tilde of k. The second term is going to give us minus alpha times psi of 0. So this psi of 0 is evaluated in the real space, though. And the right-hand side is going to be the energy that we are looking for. So this is our unknown. This is what we're looking for, psi tilde of k. So we see that instead of solving the complicated differential equation as it looked in the beginning, we now reduce the problem to solving essentially a linear equation that we know how to do from high school math. So we simply can put this psi tilde in the left hand side, this guy in the right hand side, and so we're going to have h squared k squared over 2m minus energy times psi tilde, so these two guys, and in the right hand side we're going to have plus alpha psi of 0. So the wave function, the another unknown, the wave function therefore is simply equal to alpha psi of 0 wave function in real space divided by h squared k squared over 2m minus energy. And well, in some sense this is already partially a solution to our problem. It's a solution in the sense that it determines the wave function in momentum space, and if we want, for instance, to find the wave function in real space, all we have to do is just inverse Fourier transform it back to x. But our main interest again is to answer the question of whether or not there are bound states in this potential. And so this, well, I just copy here the same equation we derived previously. So in emphasize that this is really what we're after here. So the question is, are there any available energy levels, in this shallow quantum well, which corresponds to particle being localized in the vicinity of the origin? So it turns out that this question can be answered from this equation in just two simple steps. And those of you who like mathematical puzzles, so sort of aficionados of these puzzles, may want to just stop the presentation and stare at this equation and try to come up with a trick that will allow you to figure out this energy. But if you just want to know the trick, let me show you how it works. And it's actually very neat. It doesn't require any super complicated calculations. So at this stage, let me recall that psi of x basically can be represented as the inverse Fourier transform of psi tilde of k e to the power minus I kx. So therefore, psi of 0, which appears in the right hand side of this equation, psi of 0 corresponds simply to setting x to 0 in this equation. So it's going to be an integral of all over all k over 2 pi of this psi tilde of k. So let me evaluate this integral in both sides of this equation. So if I have an equation, I can take integral of both sides of this equation. And if I do so, in the left hand side I'm going to have psi tilde of k, which per this relation gives me simply psi of 0. While in the right hand side I will have this coefficient, which is simply a constant, alpha psi of 0, an integral over k 1 over h squared k squared over 2m minus epsilon. And so the neat thing that happens here is that this we see that there is a psi of 0 that we don't really know at this stage, but this psi of 0 appears in both sides of this equation, so we can simply cancel it. And so we end up with an equation that doesn't have the wave function anymore. So it has only one unknown, and this unknown is exactly the energy we are after. So if we can solve our equation and find the value of the energy, this would imply that there exists a bound state in our potential. And remember that the bound state has a negative energy, so it must be below the continuum, and this would correspond sort of to localized particles. So we can simply put, let's say, a modulus here and a plus sign. So this would correspond to our energy we're looking for. And also, if we want sort of to restore a normal form of the integral, so we can recall that my notation was simply to save some space. So this is really what we have. So let me skip the remaining technical step, which essentially boils down just to calculating this integral, which is an elementary integral, and just present the result. And so here I sort of rewritten this equation in the sort of slightly different form, and this is the result of the calculation. So if you calculate the integral, you will see that there exists one and only one solution for the energy, and the energy is equal to minus m alpha squared over 2h squared. So alpha here, remember, alpha here is the parameter which multiplies the delta potential. So in some sense, alpha controls the strength of the potential. The smaller the alpha, the weaker the potential that acts on the particle. And the result here is that in a shallow quantum well in one dimension, or in the corresponding delta potential well, there exists one and only one bound state with this energy, which scales as so with the strength of the potential. So in the second part of this video, we're going to discuss how this result is modified in a very essential way if we go to more physical dimensions, to 2 and 3 dimensions.